The Pacific is a black, indifferent sheet tonight, swallowing moonlight and sound. Beneath that surface, spanning the distance of 3 football fields, 90,000 tons of steel moves. The USS George H.W. Bush, a nuclear-powered citadel, carrying 5,000 souls and 70 warplanes. This is the definition of sovereign power, the ultimate expression of technological mastery over the inhospitable void of the ocean. But even a floating city, powered by the boundless, silent fury of an atomic reactor, exists on a knife's edge, a terrifying dependency on the most basic element: fresh water. In the deep, thrumming belly of the ship, hundreds of feet below the flight deck, the engineering space is a labyrinth of pipes, valves, and gauges. Chief Engineer Masterson, his eyes bloodshot from a 36-hour rotation, is tracking the system that matters most right now: the feedwater line. This water is not for drinking. It is the lifeblood that flashes into high-pressure steam, turning the immense turbines that drive this colossal warship and power its electrical grid. At 3:14 Zulu, the perfect green line on the diagnostic screen, the line representing pressure integrity to the critical feed pumps, suffers a micro-hiccup, a pulse. It lasts less than half a second. It's not a failure. It's a fluctuation, a valve chatter, a tiny, insignificant blip that would be ignored in any other industrial setting. But here, 500 miles from the nearest land, it is an existential shudder. Masterson watches the gauge snap back to perfect equilibrium. But for that fleeting moment, the machine hinted at its mortality. It offered a silent, terrifying reminder. This $13 billion warship, designed to project unstoppable power across the globe, is entirely dependent on its ability to turn the toxic, corrosive ocean into life-sustaining, perfectly purified fluid. If that ability fails, the window of survival slams shut. If the desalination system dies, the Bush will not run out of fuel. It will run out of water. And then the collective, intelligent machine degrades into 5,000 vulnerable men and women adrift, facing the statistical cruelty of the open sea. We are about to analyze the invisible nervous system of the U.S. Navy's carriers, the relentless, high-stakes process of converting salt into civilization. This is the story of the liquid citadel and the immense, unseen cost of maintaining technological self-sufficiency. To understand the challenge, we must first grasp the scale. An American nuclear aircraft carrier needs to function exactly like a mid-sized, isolated town, but one that is also constantly engaging in high-intensity maneuvers and launching 30-ton aircraft. The water requirement is astronomical, approximately 400,000 gallons of fresh water produced every single day. To put that figure into perspective, 400,000 gallons is over 1.5 million liters. It's enough water to supply a small city of roughly 4,000 people. But on a carrier, every drop is budgeted according to an incredibly rigid, almost sacred hierarchy. This is the architecture of liquid duty, where some water is merely useful and some is absolutely indispensable for maintaining operational status. Tier 1. The steam citadel, 60% of production. The majority of the water, over 240,000 gallons daily, never touches a sailor's lips. This is boiler feed water. It is the most critical fluid on board, demanding near pharmaceutical purity. Salt is the mortal enemy of steam turbines and boilers. Even a slight concentration of salinity or other contaminants would lead to scaling, corrosion, and catastrophic failure of the propulsion plant. This water turns into the high-pressure steam that drives the massive screws and generates all electrical power. Zero tolerance for compromise. Tier 2. Combat endurance, 30% of production. This water supports domestic infrastructure. The ship's 4 major galleys, the laundry facilities, and showers. This is crucial for maintaining morale, sanitation, and preventing the kind of debilitating illnesses that could sideline a third of the crew. Hygiene is battle readiness. Tier 3. Sustaining life, 10% of production. The smallest percentage is potable water, the drinking supply. While essential for life, it consumes the least amount of the daily volume, thanks to rigorous conservation efforts. How does this steel city achieve this unbelievable level of production from the most toxic source imaginable? It utilizes a principle that defines the strategic advantage of the nuclear fleet, leveraging waste heat. The technology of choice on modern carriers like the Nimitz and Ford classes is primarily multi-stage flash distillation, MSF, often augmented by highly efficient multiple effect evaporators, ME. Here is the genius of the machine. 1. The abundant resource. The pressurized water reactors on the carrier produce a massive surplus of heat. This heat is primarily used to generate the steam necessary for propulsion and power, but a significant amount is available for auxiliary systems. Unlike older conventional ships that had to burn precious, limited fuel oil to boil water for distillation, the nuclear carrier gets its heating source essentially for free. 2. Vacuum magic. The MSF system doesn't boil water in the traditional sense. Instead, it sprays preheated seawater into a series of interconnected chambers, stages. Crucially, the air has been pumped out of these chambers, creating a deep vacuum. In a vacuum, the boiling point of water plummets, sometimes as low as 40 or 50 degrees Celsius, 104 to 122 degrees Fahrenheit. 3. The flash. When the warm seawater enters the vacuum chamber, it violently flashes. A fraction of the water instantly vaporizes into pure steam without requiring massive amounts of external energy. This steam is then condensed on cooling coils, forming perfectly pure, fresh water. 4. Efficiency and scale. By moving the remaining hot brine into subsequent stages, each operating at a slightly lower pressure, the heat is recycled multiple times. This cascading process allows the carrier to wring maximum purity and maximum volume from the brutal salt water, providing the daily quota of 400,000 gallons with a redundancy built in that is the envy of global shipping. The carrier's ability to generate this clean, abundant water is not just a logistical convenience. It is the unseen technological debt that buys the fleet its virtually unlimited strategic reach. But what happens when this perfect, complex machine faces the inevitable challenge of entropy and chaos? The clock is always ticking, waiting for the system to fail. The machine of salvation operates on the principle of redundancy. A modern carrier is equipped with multiple, independent distillation units. But the ocean is the primary killer, and entropy is its relentless ally. Mechanical fatigue, a cascading electrical short, or most commonly, severe scaling and internal corrosion can knock out one or more major distillers in rapid succession. Imagine the scenario. In the tropical heat of the Arabian Gulf, a catastrophic failure leads to an immediate 50% loss of production capacity. The engineers are already working the maximum feasible yield from the remaining units, but the numbers are unforgiving. The protocols for water conservation are immediate and brutal, a shift from technological self-sufficiency to human discipline. The average carrier maintains fresh water storage tanks capable of holding approximately 5 to 7 days' supply at normal consumption rates, 400,000 gallons per day. When production halves, those 7 days suddenly become the only barrier against crisis. The clock starts instantly. Phase I, immediate retrenchment. Within minutes of the casualty report, the captain institutes Code Alpha water rationing. The goal is not comfort. It is to stretch the usable reserve to 14 days, the window required for critical repairs or the rendezvous with a supply ship, oiler. The first cuts, the first 30% of production dedicated to domestic use vanishes. All non-essential water sources are cut. The ship's laundries, vital for morale on long deployments, are shut down. The 90-second rule. Showers are reduced to strictly enforced 90-second Navy showers. Turn on, get wet, turn off, lather, turn on, rinse, turn off. This isn't just a guideline. It's a protocol monitored by deck department leaders. The engine room priority, water priority remains ironclad. Tier 1, boiler feed, must be maintained, even at the cost of human comfort. Salt contamination in the steam plant is a red line that cannot be crossed, as it would cripple the ship entirely. Phase 2. The critical mode after 10 days. If the crisis persists, the situation degrades rapidly from operational stress to an existential threat. Domestic use is virtually eliminated. Water is dispensed only at specific stations and is strictly metered, enough for necessary hydration, galley operations, and critical sanitary systems. There is no showering. Basic hygiene relies entirely on pre-packaged military wipes. In the high humidity and 100-degree ambient temperatures of the engine room spaces, this swift deterioration of sanitation rapidly breeds fatigue, heat stress, and the risk of communicable disease. The ocean is the ultimate reality check. It exposes the vulnerability of the human unit. We forget that the highly specialized sailor, the linchpin of the machine, is a biological engine running on precise thermodynamic constants. Dehydration is not just thirst. It is a rapid, insidious betrayal of the cognitive system. In a flight deck environment, where coordination and split-second decision-making are paramount, dehydration is a tactical liability. Losing just 5% of body weight in water leads to severe reduction in cognitive function, reaction time, and alertness. A pilot attempting a challenging night landing, a trap, requires perfect focus. A desiccated pilot is an immediate, unacceptable risk, turning the powerful F/A-18 Super Hornet into a $70 million missile aimed at the flight deck. The machine demands peak performance, but the crisis starves the human component. The collective efficiency of the crew collapses under the weight of heat exhaustion and mental fog, proving that the carrier's vulnerability is not its armor plating, but the moist, fragile minds within. The fact that the aircraft carrier is nuclear-powered adds one final, intense layer of paranoia to the water analysis. The water is made by utilizing heat from the reactor system, a closed loop of steam generation. But what if there's a leak? What if the primary coolant, which runs through the reactor core, contaminates the system used to flash the seawater? The sailors are drinking the product of atomic engineering. This is why the purity protocol is non-negotiable and utterly relentless. Samples of potable water are drawn and tested hourly throughout the day, every day, by specialized engineering laboratory technicians. They are not merely testing for salinity or bacteria. They are monitoring for even trace amounts of radiation, measured in parts per million, ppm, or even parts per billion. This is the ultimate contract of trust between the Navy and its crew. We are providing you with total technological autonomy, but we must guarantee that the very water sustaining you is not slowly poisoning you. The machine must not only generate life, it must certify its innocence against the spectral threat of the nuclear core. This constant, painstaking scrutiny is the operational price of our self-sufficiency. The massive water production of a modern nuclear carrier is not an accident of design. It is the direct, evolutionary answer to centuries of naval strategic vulnerability. The history of maritime power is littered with moments where the absence of water, not enemy fire, was the ultimate operational constraint. In the age of early steam power, distillation was technically possible but brutally inefficient. Conventional warships of the early 20th century used precious boiler fuel, oil, or coal to boil seawater. This created a terrible strategic bottleneck. The choice: a captain often had to choose between maximum speed, consuming fuel for propulsion, and maximum endurance, consuming fuel for water production. Every calorie burned for freshwater production was a mile subtracted from the ship's strategic radius. Logistical slavery. These ships could not be truly self-sufficient. They were perpetually chained to logistical chains, forced to rendezvous with tenders or enter foreign ports simply to replenish fresh water for the crew and, critically, for their steam plants. Their strategic independence was a mirage, easily broken by a scarcity of H2O. The nuclear-powered carrier broke this logistical chain. By providing an essentially infinite cost-free heat source, the engineers were suddenly freed to focus on maximum efficiency and purity, rather than conservation of fuel. This technological leap transformed the carrier from a powerful ship into a truly autonomous, global-reach citadel. However, Technology only expands the window of survival. It does not eliminate the fight. The system that turns salt into life requires a relentless, almost maniacal level of human intervention. The engineers of the A-Gang, Auxiliary Division, and EDV, Electrical Division, are locked in a perpetual battle with the physics of the ocean. The primary adversary, chemical aggression. Salt water heated to high temperatures is chemically aggressive. The process of flashing and boiling leaves behind concentrated brine, which quickly forms scale, a rock-hard deposit of mineral buildup, on the interior walls and hundreds of miles of piping inside the evaporators. This scale is the cancer of the system. 1. Scaling destroys efficiency. Scale acts as an insulator, preventing heat transfer and dramatically reducing the efficiency and volume of freshwater produced. 2. Scaling causes failure. If left untreated, scale causes uneven heating, localized overheating, and eventual corrosion, leading to catastrophic pipe rupture. The cost of this water, therefore, is not measured in fuel, but in human capital and man-hours. Maintaining the distillers is a grueling, non-stop procedure. Engineers must frequently shut down units, open the massive pressure chambers, and physically enter the vessels to chip, scrape, and chemically clean the internal tubes and shell plates. This is the unglamorous, dirty work of preserving the machine of salvation. The technological debt paid daily by exhausted sailors in hot, cramped conditions. Modernization has introduced a powerful layer of digital vigilance to this ancient problem. The current generation of carriers relies on sophisticated monitoring systems, often PLC/SCADA, that form the collective mind overseeing the water flow. These systems do not replace the sailor, but they amplify their capability. Predictive maintenance. Sensors track temperatures, flows, and conductivity across hundreds of points within the distillers. They can detect a subtle drop in heat transfer efficiency, the first sign of scale buildup, long before a human could spot a performance degradation. The purity standard. The system's primary function is ensuring the pristine quality of the boiler feedwater. If the conductivity, a measure of residual salinity, exceeds a threshold as minute as 1 part per million, ppm, automatic diverter valves kick in, shunting the contaminated water back into the brine disposal system. No risks are taken. The machine is programmed to prefer zero water over slightly impure water, safeguarding the propulsion system above all else. The evolution of naval water production is a story of optimization, fueled by free heat and enforced by digital precision. It allows the carrier to transcend the limitations of logistics, transforming the vast, poisonous ocean into a strategic asset. But the fight remains. The system must be perfect because the moment of failure represents the moment the clock begins its rapid, brutal countdown to dehydration and operational collapse. The momentary pressure drop that startled Chief Masterson in the hook has been neutralized. The automatic controls compensated. The auxiliary pumps kicked in. The system, once again, achieved equilibrium. But there is no celebration in the engineering spaces, only the constant, humid realization that the fight with entropy has only paused. Masterson looks at the gauges, showing 400,000 gallons flowing through the purification stages. This enormous daily volume of life-giving water is the true, hidden measure of strategic power. The ability of a U.S. Navy aircraft carrier to sustain 5,000 people at peak performance, thousands of miles from any stable harbor, is arguably the most profound feat of logistical engineering in modern warfare. It proves that the floating city is not just a collection of steel and aircraft. It is a perfectly engineered, self-contained biome. This water system is the ultimate metaphor for the ethos of the entire fleet. It must be unyielding, redundant, and perfect. The 400,000 gallons produced every 24 hours is the physical embodiment of the Navy's technological debt. It is the daily payment required to maintain operational autonomy. We have mastered the physics of the atom to generate the steam, and we have mastered the physics of vacuum to distill the water. But this mastery demands absolute vigilance. The moment the machine stops generating water with perfect purity, Two disastrous clocks begin running simultaneously. 1. The operational clock. Contamination ruins the propulsion plant, turning the 90,000-ton warship into an expensive, vulnerable raft. 2. The biological clock. Dehydration cripples the crew, turning the highly trained sailor into a vulnerable unit incapable of executing complex, high-stakes tasks. The ship's distillation system is the invisible nerve that connects the mission to the sailor. No matter how powerful the F-35s are, or how deep the reactor's core runs, all strategic calculus collapses if the crew cannot drink, cannot cool the boilers, and cannot maintain sanitation. The ultimate achievement of the system is that it makes the crew forget the terrifying reality outside the hull. The air conditioning works. The mess hall serves hot food. The drinking fountains dispense cool, clean, non-radioactive water. This technological shield against the chaos of the ocean is the most fundamental aspect of the nobody left behind philosophy. It begins not with a rescue swimmer in the sea, but with the engineer ensuring that 5,000 sailors will not perish from thirst before they ever face an enemy. We began with a sudden, near-silent drop in pressure, a brief moment when the relentless machine of salvation faltered. We end with the understanding that this complexity, this massive scale of water production, is the true price of duty. The technology of multi-stage flash distillation, powered by the boundless thermal energy of a nuclear reactor, has successfully extended our window of survival and amplified our strategic reach to the ends of the earth. But the fundamental law of the ocean remains immutable. It is vast, corrosive, and unforgiving. Our readiness to confront that reality, to perpetually outweat salinity and corrosion, and to dedicate immense human and technological resources to ensure perfect, potable water flow, is not just logistics. It is liquid resilience. It is the foundation upon which the entire projection of global power rests. The 400,000 gallons produced daily are not merely water. They are sustained civilization carved out of the hostile, primary reality of the deep blue sea. And the engineers who keep those clear streams flowing are the unsung guarantors of the fleet's sovereignty.